Also, there might be some light dog barking in the background. I apologize for that as well. Um, but to kind of piggyback on what Sebastian was talking about, you know, we're focusing on these two really exciting new technologies to address the kind of longstanding issues of autonomous vehicles needing to operate in the real world, which is incredibly complex and incredibly unpredictable. So to start this talk with a pretty obvious statement, autonomous vehicles are hard. We like to call them one of the most complex AI challenges of our time. And this is primarily for two reasons. One of which, with classical stacks, we have taught them to kind of follow the rules of the road in a pretty black and white way. You see a stop sign, you stop. You see lane lines, you stay in the middle of them. But what happens if the lane line is in the middle of the lane because there are traffic cones and a temporary stop sign? These sort of split-second decisions you need to make and adjust to as a human driver are a lot harder for a classical machine learning stack to be able to adjust to. In addition, a lot of the situations we want these vehicles to be able to handle are dangerous. You have near miss scenarios, you have vulnerable road users, data that you don't necessarily want to collect in the real world, but you really need your vehicle to be able to handle. So we see data as the answer to solving these problems. And this isn't just for autonomous vehicles. This is true for robotics, humanoid robots that are starting to really get off the ground, AMRs operating in warehouse environments. The world we live in is pretty complex. So we need the data that we train, test, and validate these machines on to accurately represent this complexity, as well as do so with high fidelity. Traditionally it's been a mix of real world data and also simulation. But simulation that achieves the fidelity we need traditionally has been pretty arduous. It requires dedicated infrastructure as well as artist generated content. It can take a long time to reach the level we need for it to actually be effective. But recent breakthroughs in generative AI, specifically neural reconstruction and generative models, have allowed us to kind of leapfrog over the need for manual simulation and address the data problem head on. In addition to data, we see kind of the three computers as key to being able to deploy physical AI at scale. And these three computers are the data center where we train the AV stack or robotic stack. Then we have simulation, which again is a combination of digital twins and world models where we can test and validate the stack. And then finally, we have the embedded compute that runs in the car or robot, operating in real time as the vehicle or machine navigates the real world. This talk specifically is going to focus on the second computer. Data kind of flows through all three of these computers, but the second computer is really where we bring in the data, generate it, and where it kind of refines and makes the model ready to handle the real world. So here's kind of a zoomed out view of how we use neural reconstruction or world models in this data flywheel. And they're all anchored by either our suite of Cosmos World Foundation models or our Omniverse libraries for digital twin construction. So it starts with data processing. In here, we use our Cosmos Reason VLM to allow us to take massive video data sets and pare them down to curated, targeted data sets we can use to post-train for specific tasks, refine the model, address weaknesses we've seen in the real world. And then we can use our vector-based search workflows to take out the needle in the haystack scenarios that we want to really make sure our vehicle can handle. Once we've created these data sets, we can then bring it into interactive simulation using our Omniverse neural reconstruction technologies. With that, we're able to not just replay the scenario as we experienced it in the real world, but make adjustments, either change the trajectory of the vehicle, adjust sensors so you can scale it to any vehicle body type. We can add new objects, all the sorts of variety that happen in the real world, we can now bring into simulation relatively easily. We can then scale that data even further using our world foundation models, Cosmos Predict and Cosmos Transfer. Predict and Transfer are both autoregressive to diffusion models that can take in image, text, or video data and then scale it in two different ways. Predict can take those inputs and then generate entirely new world states. So we can take, 6 images from cameras around a vehicle and create an entirely new scenario. So it allows us to take a small amount of real world data and turn it into a pretty rich data set. And then we can scale that data set even further with transfer, which is a style transfer model, where we can add new weather, lighting, and geolocations to be able to cover all of the ODDs you'd want to be operating in for your robotaxi or autonomous vehicle service. And then finally, we bring Cosmos Reason back into the loop to go over all of this new data we've generated and tell us, A, whether it's realistic enough and matches the laws of physics so the stack can translate from simulation to the real world, as well as if it's challenging enough. We want this data to be useful. We don't just want to throw random data um, random data to it that's not going to improve and make the stack truly robust. We need to make sure it's actually targeting the weaknesses or capabilities we want to enable. So Reason really helps us do that before we then test the stack and reiterate and continuously improve as we go through real world operation. So to kind of dive in deeper into each of these components, um, when we start with the data processing part, the core of this, as I said before, is Cosmos Reason. And Cosmos Reason is a really important component, not just for our testing and evaluation side, but also operation inside the vehicle. We're not going to get too much into in-vehicle operation, but we do use Cosmos Reason as part of our reasoning VLA backbone in the vehicle, which allows us to address sort of the nuances of the real world that I mentioned earlier that are such a problem for classical AV stacks. And what Reason does is it adds reasoning traces to the path planning of the vehicle. So in the situation we outlined earlier with the construction zone, it can take in the context of the construction cone or the traffic cones it's just driven by and say, okay, I am in a construction zone. I should nudge over to the left to give the construction zone some space and slow down because there's a high likelihood a construction worker will cross my path. Um, so this allows us to, act more flexibly in the real world than a traditional stack. Then we can then use this same architecture to go through these massive data sets and output reasoning and add annotations and captions that we can then use to curate the data further. So here's a look at how that annotation and captioning works. So here's a relatively complex scene for an AV. We have a temporary stop sign, a vulnerable road user, a stopped vehicle, and then an oncoming ambulance. Using those reasoning traces, Cosmos Reason can go through and write a pretty detailed description of what's happening and then condense it even further so we can have a pretty easy way to go through clips quickly. And another benefit of this natural language description of these scenes is it also gives us a look inside how the model thinks and reasons through things. So if there are weaknesses or it's misunderstanding things or not making the right connections, we can catch it pretty quickly and address it in our testing and validation. So we then add these annotation capabilities into our curation pipeline. So Cosmos Curator is a GPU accelerated curation workflow that allows us to deduplicate video, filter through clip videos to just scenarios of interest, and then add these annotations and video and text embedding. It significantly accelerates the curation process. If you were to take 20 million hours of video, which also happens to be the same amount of data we used to pre-train Cosmos, it equals about 34 terabytes of data. If you were to try to annotate and curate that on your own, purely through human processes and CPUs, it would take about 3.5 years. With this GPU accelerated workflows, and sorry if you could, my dog's coming through a lot. Um, with the GPU accelerated workflows, as well as reasoning VLMs, we can accelerate that process to a matter of 40 days. So it's a really significant time and cost saver. And then once we've curated these data sets, we then can use our Cosmos dataset search, another GPU accelerated workflow based on Cosmos Reason. CDS is a vector-based workflow search that allows us, that uses the embeddings and annotations from Cosmos Reason to allow us to quickly pull out these needles in the massive haystacks. So the example shown here are these trucks double parked on the street, a very common urban driving scenario, but one that is really hard for autonomous vehicles to figure out. So we can create these targeted data sets and really address the weaknesses very quickly. And curator and CDS work hand in hand together to make the data processing workflow pretty seamless and much quicker than we've been doing in traditional A/B development. We also use these tools internally for our own development and have found that by using vector-based search, we can go through hundreds of petabytes of data and using hundreds of thousands of queries, we can speed up our data discovery for these edge cases, rare scenarios, up to 20 times. Again, saving a very significant amount of time and effort. Okay, so now that we have our data set, we want to bring it into simulation. And we do this with our NeurEC neural reconstruction libraries, which compared to the manual simulation process are light years ahead in progress of what we're able to do. We can take this recorded log data, as I mentioned earlier, replay, adjust, but maintain the fidelity of the real world drive itself, which is really huge. And NeurEC is not just a single technology, it's a three categories of APIs and libraries that are entirely composable. So you can take what you need and integrate it into your own workflow or use it together as a unified workflow. So these include our reconstruction libraries. So our reconstruction container that can take the raw sensor data and transform it into our Gaussian-based data formats. We then have our rendering API, NREND, which can take the Gaussians and render out data in USD format to make it pretty standardized to most simulation platforms like Carla or IsaacSim. And then we have our generative enhancement models, which can improve the appearance and the quality of the reconstruction, addressing the black holes or blurriness, or making added objects look more natural to the scene. And one of these generative models are Omniverse NeurIPS Fixer. We actually just released last week at NeurIPS for NeurIPS Fixer, which it is now generally available on Hugging Face, and it is built on our Cosmos Predict model. And what Fixer does is it can take a reconstruction, and if you are generating novel views or if the reconstruction quality itself isn't great, it can use Predict to generate the world state of what it thinks should be there and use that kind of fixed video to reconstruct the data, leaving you with a much higher quality simulation. So Fixer can run in the loop. So offline, once you've generated the reconstruction, you can then reconstruct it using Fixer, or it can run alongside the renderer for kind of real-time fixing. Both the model and post-training scripts are available on Hugging Face. We pre-train Fixer mostly with autonomous vehicle data, but it can be used for robotics. It just requires some additional post-training. So then this is kind of how it all fits together as an architecture. As I mentioned, it's entirely composable. Our reconstruction containers and libraries are currently in early access, but we're working with ISV partners to make them available in those workflows. Our rendering API is integrated into the Carla open source AV simulator, as well as Omniverse Kit and Isaac Sim. And then Fixer can is available independently. It works well with Neuralink, but can also work with other neural reconstruction pipelines. It's entirely agnostic to whatever you're using. And then our asset harvester is coming soon. Okay, now we have our simulation. We've been running kind of different versions of it, but now we want to scale the data even further. So this is where the other two models in the Cosmos family come into play. So first we have our Cosmos Predict model, which can generate up to 30 seconds of entirely new world states using simply image, text, or shorter video data. Um, it can work entirely across multiple sensors on the vehicle. So if it generates an oncoming vehicle, you'll see it pass by in the side cameras, in the rear view camera, in the exact same consistency that you would see if you were using a real data collection. Our most recent generation of Cosmos Predict 2.5, is now available on GitHub and Hugging Face, as well as post-training scripts. Again, both Predict and Transfer were mostly pre-trained on AV, as well as robotics data. So they work pretty well out of the box for AV, but depending on your use case, may require additional post-training. And then we have Transfer, which then kind of allows us to explode our data in terms of lighting, weather, geolocation. And it can input um, majority of the formats of the data formats we're dealing with AV development, whether that be structured, visual, or geometric data, LiDAR scans, HD maps, or even just RGB data. You can take that in and then kind of go crazy with whatever you want to generate. It can be as simple as a different season, or as wild as flaming vehicles and a blizzard in the middle of Florida. Kind of the world is your oyster in terms of what you want to generate and what could be relevant to your test case. Similar to Predict, it is openly available on Hugging Face and GitHub. And our latest generation is built on Predict, so it can also generate up to 30 seconds of video across multiple cameras on the video on the vehicle. Now, a question I frequently get when talking about Transfer and Predict is, does it handle other sensor modalities, especially when we're dealing with autonomous vehicle development? While the core models right now primarily output camera data, we are starting to get into these other modalities. So we just released LiDAR Gen, which is a model post-trained from Cosmos Predict that can take in multi-camera RGB data and output LiDAR point clouds. Again, this model is also available in the same repos as our core models. However, it does need to be post-trained on your specific sensor setup and sensor parameters, but we do provide post-training scripts to help you kind of get off the ground with these generations. Okay, now that we've generated our massive new data set, we bring Cosmos Reason back into play to then let us know how high quality is this data? Is this actually what we need? And will it be useful in translating simulation to the real world? So we run the data through Cosmos Reason, and using the exact same kind of reasoning trace process, it can go through and say, all right, the car is driving among traffic pretty normally, but then all of a sudden it runs into a divider and disappears and regenerates like a video game character. That doesn't really happen in real life. On top of that, when it hits the divider, the motion doesn't really change. You don't go over the bump in the same way you would in the real world. Thus, this video, while a relatively interesting edge case, isn't really useful for what we're trying to do because it won't teach the car how the world actually acts. So we should throw it out and kind of whittle our data set down. So Cosmos Reason is really kind of the anchor towards making sure the data we're using is actually what we want and taking these unwieldy massive data sets and turning them into really powerful tools for testing and validation. Um, Now, to make these technologies available to the industry, we want to make them available in tool chains that you're already using. So we work really closely with ISV partners such as Voxel 51 to make Cosmos and Direct pretty readily available. And what Voxel allows us to do is to make sure that the data we're inputting into this data flywheel is clean and can actually generate nice reconstructions that we can then scale out further with Cosmos. Um, Again, we can't just be training these vehicles with any data. We put garbage data in, we're going to get garbage out. And Voxel helps us clean this data up, make sure it's quality, high fidelity, so that you're not just churning through the iterations over and over and over again. And then we also have Cosmos Transfer available in the tool chain, so you can run those data amplifications all in one place. We also work with Fortelix, which can generate interesting scenarios in object level simulation, either from log data or from your own sort of data repository. We can then generate that in high fidelity sensor simulation using Omniverse and scale further using Cosmos Transfer. We're also working with MCity, the University of Michigan's autonomous vehicle test track, to enable a similar pipeline where we can take their existing test track in Ann Arbor and scale out the data first, again, using sensor simulation and then Cosmos Transfer. I'm based in Michigan and it has been really cold and snowy and not super pleasant. So it's been really fun to look at the transfer generations and imagine this area on a nice, warm, sunny day. So transfer is not only useful for autonomous vehicle testing and validation, but for seasonal sadness. Um, and then we are also making these technologies available to individual developers and researchers or just general Carla users through these integrations that I mentioned earlier. So Nurek rendering is available in Carla. You can take pre-reconstructed scenes. We now have about 1,000 of them in our physical AI open data set, which I'll get to in a few slides. And you can take those scenes and render them out in Carla, again, in that interactive simulation where you can make adjustments and not just be limited to pure replay. We also have a similar Cosmos Transfer integration as well. The QR code will point you to a Brev launchable, which creates a pretty easy one-click interface to access the compute you would need to run transfer on your own setup. We also have a recently released Cosmos cookbook. We are super excited about this. Um, Cosmos, even though it feels like it's been around for a while, it's really only been a year, and we are really curious to see how the community is using it. So we have this GitHub repo where our own developers and our partners, including Voxel 51, have been publishing these step-by-step recipes for ways they've either post-trained Cosmos, generated data with it, applied it to different use cases that you can then replicate. And we also invite you to submit your own. We want to know what you're doing with it, and we want to bring it to the community. This truly is intended to be a community resource. So please let us know how it's going and how you'd like to contribute. And then finally, I started this talk saying that data is the answer to this autonomous vehicle problem. And we happen to have a lot of data. As a relatively large company with a lot of physical AI research and development happening, we generate and collect a lot of data. So we want to make that data available to the community. So starting with our previous GTC in March, we've begun to release the data we've been using in our own development on Hugging Face. So this includes robotics trajectories, both generated and in the real world, as well as driving data. We just released our first real driving data set back in October, which is super exciting. It's about 270,000 20-second clips. covering ODDs in the US and Europe. Really encourage you to check it out. It's a great way to kind of start the data flywheel I outlined at the beginning. We also are releasing USD SIM ready assets. So it's kind of a, not necessarily a junk drawer, but a toolbox full of objects and different sort of items you can use to create a fun obstacle course for your autonomous vehicle testing and validation. So with that, I think that's the end of my presentation and happy to take any questions.